In this video, we're going to talk about reducing radicals. So there are really two ways to reduce radicals, and I'll tell you my preference. I prefer this first way called the radical tree. So what we do here, if we have this example, maybe the square root of 72, we immediately try to think about perfect squares. So when I say perfect squares, I think about the first few numbers. If they were to be squared, what are those? So 2 squared is 4, 3 squared is 9, 4 squared is 16, and so on. So I'm thinking about these numbers here as perfect squares, because then if we go the other way, obviously the square root of 4 gets us back to 2. So that would reduce some of these radicals. Square root of 9 equals 3, and so on. So I don't have to look for perfect squares, but it certainly helps things go faster. So immediately 72, I think, well, I know that is a factor, has a factor of 9. So I'm going to immediately put 8 and 9. And then I can just keep going. What are some factors of 8? I know that is 4 and 2. And if I keep going with 9, I know that is 3 and 3. So what I like to do with the trees, just go down as far as I can go. If I recognize them as perfect squares, I could stop there or just keep going. The key with the tree is that I need to find 2 of something. And every 2 or pair of something, every 2 of the same number, I get to bring 1 out. So for this pair of 2's, I can bring 1 2 out. For this set of 3's, I can bring 1 3 out, and we bring it out into the front. And anything left on the bottom branches, I square. So if he doesn't make a pair with anybody, then he stands alone. And he is what will be underneath the radical. So we multiply the things in the front that we bring out. So this would become a 6 on the outside, and a 2 is left on the inside. So that would be our final reduced radical. So square root of 72 is the same as 6 square roots of 2. We could go a step further, and if we go higher up and recognize these higher up squares, so 5 squared is 25, 6 squared is 36. These would be good to memorize, kind of all of your perfect squares up to 12. Those are all really good ones to have in your memory. So here, if I could have remembered, and again, it didn't matter, we got there anyway, but a quicker way would have been if I immediately saw, oh, I know 36 and 2 makes 72. And I would recognize that 36 is a perfect square. I could keep going in my tree, and a 6 would come out and a 2 would be left over. So same thing, we would get the same result here. Another way to think about this, so in the same problem, some people prefer not to go downward. So depending maybe on your paper, if you have more room, kind of going left to right, you could do it this way, or if you prefer, if the tree doesn't quite make sense or resonate with you, this would be another method. So another way to think about it is going this way. So using those same factors, I can write radicals like this. And our rule of radicals is I can separate them, or thinking going the other way, when I have 2 separate radicals that are just being multiplied, I can put them under the same radical. So it's kind of going the opposite way. And when I do that, I recognize that I've broken this up. Square root of 8, I'm not really sure about that yet, but square root of 9, I immediately see that as 3. So that becomes 3. So far we have 3 and then a square root of 8. We always put the whole number or the regular number on in the front, the integer, and then the radical obviously after that. So for this one, I know 8, I could think about that. So some more, I could say, okay, I know the 8 is 4 and 2. So that's square root of 4, square root of 2. Well, I know this is 2. Square root of 4 is 2. So that's how we also end up with 6 square roots of 2. So we get to the same result, just in a little bit different way, and kind of using the space to the right here as we move kind of horizontally. So that would be a different method as opposed to the tree. I kind of prefer the tree because to me, it feels like you're catching everything, right? You're kind of going about it and can visualize all the factors. This way, if you're going to the right, it kind of feels like things could get lost, right? Whereas it's all down on the tree, you're all going down and you can kind of see the bigger picture. I don't know, it kind of makes more sense to me. So those are two methods for reducing radicals. So if we try another one, square root of 80, let's try. If we think about two factors of 80, immediately I think of 8 and 10. And again, it doesn't matter where you start. If you try to think about perfect squares, that might get you there faster, but it'll always end up the same. So if I just keep going, I know that's 4 and 2. So you can just keep going until you can't go any further. So 5, there's really only 5 and 1, and 2, only 2 and 1. And 4, I recognize that as a perfect square, and so I could stop there or just write it down below that I have 2 of those. Now I have 2 separate branches, and that's okay. I still have 2 2's. So that counts. That's a pair of 2's. So this would count as a pair of 2's. I get to bring one out. And this would count as a second pair of 2's. So I would bring one of those out. And the 5 remains underneath. So that would be 4 on the outside and a square root of 5 underneath. And he can't be reduced any further. So that would be that would be our final answer for that one. So those are two ways and two different examples of just simplifying radicals. Now, if we have something on the outside, we didn't talk about that, but if I had like a 3 square root of 32, given as the problem. Immediately, I would think, okay, I know that is 4 and 8. Or I could think about even further, I could think about 16 and 2. That way, 16 is a perfect square. That gets me 2 4's, and a 2 would stay on the inside. So if there's already a number out front, I'm just going to take whatever comes out and multiply it by that. So 1 4 comes out, and the 2 remains underneath. So that would be a 12 on the outside and a square root of 2 on the inside. And same thing, if I had started with those other factors, it doesn't matter where you start. So if I could only think of 8 and 4, I can just keep going. So this would be 4 and 2. I could stop there and see my two 4's. Or if I didn't recognize that, I could keep going and see all of the 2's. So here I have one set of 2, I would bring one out. And here I have another set of 2's, and I would bring one more out. And then this 2 would remain underneath. So that would be 4 on the outside, and I still had the original 3. 4 times 3 is 12, and the 2 remained underneath. So no matter which way you go about it, as long as you keep going down the branches, you should get to the same answer. So now let's talk about adding and subtracting, just to review the radical rules. So if I have a square root of 4 and I'm adding it to a square root of 3, I cannot add those. Those are just two different animals. So there would be nothing there except obviously this is 2. So that would be 2 plus square root of 3. That would be all I can do. If it wasn't such a nice radical, if this was square root of 5 plus square root of 3, there's nothing further I can reduce there. That would just be square root of 5 plus square root of 3. I can't combine those if I'm adding two different radicals. If they are the same radical, then those are the same things I can add. So this would be like a 1, invisible 1 out here. That would be 1 of something plus 2 of something. That would just be 3 of those somethings. So in that case, if they're the same radical, I can combine those. So oftentimes we're given problems where we want to reduce and combine. So if I have an example here, so 24 is not a perfect square, so I'm going to try to reduce that. So immediately I think of 4 and 6. That would be 2 and 2. 6, unfortunately, it looks like it can be reduced, but it really can't. 3 and 2 doesn't really help us, unless it's combined with another 2 or something. So in this case, I have 2 2's. I can bring 1 out. That would be a 2 in the front. So this would become 6, and these 2 don't really help, so really I'm squaring the 6. So that would be 6 square roots of 6. And now 81, I know that is a perfect square, so that would just become 9. So this would be 3 times 9, which would be 27. So that would be as much as I could reduce that one. So that wasn't one that we could combine, but oftentimes they would want you to reduce so that you could combine them. So this might be an example of that. So if we have 4 square roots of 3 minus square root of 27, so this would be one we might immediately say, okay, 3, I can't really reduce him. But it's a good start to me thinking about, gosh, if I could get this as a square root of 3, then I could combine some things. So I really want to get him reduced to square root of 3 if I can. And I do know that 3 goes into 27. So immediately I think of 3 times 9. And yep, sure enough, 9 is a perfect square. That gets me 2 3's. So 1 3 would come out. So this would become 3 on the outside, and a 3 would remain on the inside. So we would have 4 square roots of 3 minus 3 square roots of 3. That would just be 1 square root of 3 left over. And we don't have to write the 1. It could just be square root of 3. So when we're adding or subtracting, we have to have the same radical, same number underneath the radical in order to combine them. Otherwise, we would just keep them separate. So that's adding or subtracting. Now, like we talked about before, if I have 2 numbers and I'm multiplying, I can just combine those under one radical. So I could either go ahead and do that and then try to reduce this if you're asked to give everything into reduced radical form, which is usually the case, or I could try to reduce at the beginning. And in this case, 10 doesn't reduce. It feels like it could, but we end up having over here, this is easier to think about reducing these two. And since we're multiplying and they end up over here under the same tree, I can combine those same trees or those pairs if I have a pair. So that would bring 1 2 out. So I would have a 2 out front, and then it looks like I have a 5 and a 7. That would be a 35 underneath. And I could check my work here. That would mean this would have to be a 4 and a 35. So I don't know that off the top of my head, but if I use a calculator to check, that should be 4 times 35. Yep, is 140. So that would be how we get here. That would be a 2 and a 2. The 2 comes out and the 35 remains underneath. Sometimes it's easier to think about smaller numbers and their factors and reduce from there as opposed to a giant number. It's not that giant, but right, 140. I don't often keep factors of 140 in my head. So that would be 2 square roots of 35 there for that. So just to review, the rules of radicals are, if I add them, they have to be the same radical. If I multiply them, they can be different, and I can combine them under one radical. So in this case, that would just be square root of 10. Now let's quick talk about dividing radicals. So if I have, let's say, square root of 32 over square root of 4, they probably wouldn't give you that, but right, just in case. Same with our multiplying rule. When I'm dividing, I can combine those under one radical and then just do that operation. So just like if we were multiplying, this would be just combining them under one radical. So 32 times 4. And that would be, let's see, what is 32 times 120? 128? Yeah, 128. So in the same way, doing division, I can combine it under one radical, and that would just be the square root of 8, because 32 divided by 4. Then we probably always want to keep it in reduced radical. So again, I could do my tree. I know that is 2 and 2. So a 2 comes out, and a 2 remains underneath. So this would be 2 square roots of 2. So let's do one that would give us a radical in the bottom that would remain. So if we did something like this, whereas even if I combine that under one radical, it doesn't reduce super quickly or nicely, right? So 48 does not divide by 10. So I can think about them separately. So if we were given this, or if we were given them as one, we could certainly just separate them back out. And it makes more sense to think about reducing 48 and 10 in our little tree. So radical 10, we already know does not reduce. 5 and 2, that doesn't help us. So 48, though, I could think about square root of 48 and do the tree. That would be 4 and 12, and that also gets me another 4 and a 3. So here I have 2 4s, and a 3 would remain. So a 4 comes out. I'm going to replace this guy with 4 square roots of 3. So we probably wouldn't want to leave it like this. Often teachers say we don't want any radicals in the bottom. So we would want to, it's called rationalize the radical. And what that means is I'm just going to multiply the top and the bottom by the same radical that's already in the bottom. Because we can see here, square root of 10 over square root of 10, that's just 1. So I'm just multiplying the whole equation by 1, which doesn't change the value. It just changes how it looks. So when I do that, we'll talk about the bottom first. The square root of 10, essentially squared, right? Square root of 10 times square root of 10 is just 10. This is like going forwards and backwards. If we think about a nice perfect square, the square root of 4 is 2. Then if I were to square that, 2 squared, now I'm back to 4. So when I square a square root, I'm left with that same something. Or if I take the square root of something squared, same thing. 2 squared and the square root of that would get me back to 2. That would be 4, square root of 4 gets me back to 2. So it's kind of like the square and the square root cancel each other out. And when we start to talk about x, you may have already started to talk about x, but the square root of x squared gets me to x. So sometimes when we're solving for x, we can do a square root to get rid of the square, or vice versa, we can square a square root to get rid of it if we need to solve. So this is what's nice about rationalizing the radical. That just gets me that number on the bottom. So the square root of 10 squared is just 10. I'm back to that same something. So that's just a nice whole number on the bottom. And then up top, again, I can combine under one radical. So that would just be 4 square root of 30. And unfortunately, I don't think 30 reduces with anything. So we could leave it like that. 4 over 10 does reduce. We can reduce those by 2. That would be 2 square root of 30 over 5. And that would be our nicely reduced radical. Yeah, because 30, right, we can't take any perfect squares out. 4, 9, 16, no. So that's always a good check too, is to check those perfect squares and try to think about my lowest perfect square is a 4. So if your number can't be divided by 4, most likely it is not going to be reduced when we're talking about these higher up, larger numbers. So that would be our reduced radical there. So those are reducing radicals, simplifying radicals, and using the radical rules to add, subtract, multiply, and divide. Feel free to comment below with any of your questions or different methods you have found helpful to reduce radicals.